Hello friends, this video on chemical bonding part 12 is brought to you by examfear.com. No more fear from exam. Before watching this video, please make sure that you have watched part 1 to part 11. The reason why we studied this is because we'll discuss the bond parameter, the type of bond, which bond is weaker, which is stronger, and all this. So there are some parameters to define the bond. There are something called bond length, bond angle, bond enthalpy, bond order, bond structure, and the polarity of bonds. These are some of the bond parameters. For example, for a student, what is parameter? The parameter will be the student name, the student age, student sex, there's a male or female, and student class, this is the class is, or you can have a student's height. So these are the parameters which determine the student. Right? A student you can have, or student's roll number. A lot of schools have this roll number. So a student can be classified using his name, age, sex, class, height, roll number. You can find the students, right? So the parameters for a student. Similarly, for a bond, these are the parameters we talk about. We talk about the bond length, we talk about the bond angle, we talk about the energy released or required to break a bond, we talk about the bond order, the number of bond. We talk about the resonance structure also in the bond, which makes the whole molecule a little more stable, and we talk about the polarity of bonds also. Right? There is charged or non-charged. We'll discuss all these bond parameters now. So let's understand that these parameters are required for us to have a better understanding of the bonds. Similar to this case, for example, if you have the name, age, and all these parameters for a student, you tend to understand student better, right? Or how much marks he got in the last exams. So with these you can understand the student better. Similarly, with these parameters, bond length, bond angle, bond enthalpy, bond order, resonance structure, polarity of bonds, you can understand the bond better. So let's start with the bond length. Bond length is nothing but the equilibrium distance between two bonded atoms in a molecule. As I told, one molecule has n number of bonds. So in a molecule, if I have two atoms and the equilibrium distance between these two atoms in a molecule is called the bond length. Typically, if the covalent radii, please note, the covalent radii I am talking about, we'll discuss the types of radius actually, the non-covalent radius, covalent radius, and different kind of radius. So if the covalent radius of the two atoms are Ra and Rb, then the bond length is Ra plus Rb. So you see in this case, this is Ra and this is Rb. The bond length is this plus this. And how do we find the bond length? So using spectroscopic, X-ray diffraction, electron diffraction, there are various techniques given by the physics world actually. So these techniques help us to find the bond length experimentally. So in the lab, if you have, let's suppose, oxygen molecule, or let's suppose you have HCl, you can take any molecule and if you want to find the bond length, you can use these techniques to find the bond length. I'm not sure in your lab this techniques are available, but these techniques are used to find the bond length. And some bond length are given. For example, OH bond length is 96 picometer, CH is 107, NO is 137. So we have different kind of bond. Also, if you see carbon-carbon bond, single bond is 154. When we talk about double bond, the length decrease. When we talk about triple bond, the length decreases further. So these are the experimented value, I'll say. Experimented found value of the bond length for various bond which we use in our day-to-day chemistry. You don't need to learn this or mug up this, just understand that these values can be experimentally found using these techniques, and we have some bond length already known to us. As I used the word covalent radii, so let's talk about the various atomic radii. The first type of atomic radii is the covalent radius. So this is the radius of the atom's core. Please note, is the radius of the atom core. So for example, in this case, you see, this is my covalent radius, 99. The total is 198. So I have two atoms in a molecule and they are totally stuck together. Total distance I'll find between two molecules, divide by 2, I'll get this distance. That is my covalent radii. and it is the radius of atom's core, right? Then we have something called van der Waals radii. This represents the whole size of atom and includes the valence shell also. We'll understand more this when we talk about van der Waals force, which is the force or attraction between two molecules. So let's suppose I have one molecule, oxygen molecule. I have one more oxygen molecule. But when you see oxygen, let's suppose if you see oxygen, there are a bunch of oxygen molecules, right? A bunch of oxygen molecules, and they are held by some force, and that force is van der Waals force. We'll discuss in the next chapter the van der Waals force, which ties up different molecules. Right? If you want to recap, I can give you a recap. So if you talk about the atom, in the atom you have this nucleus, and then you have electrons, right? They are held up with some force. So this has a positive charge, a negative charge. They held up with the positive and negative coulombic force. And then we have with atoms, this atom you have a more atom, right? And they are held again with a force. Those I'm talking, we are discussing about those forces, right? The electron sharing and sometimes the electron transfer, and we get molecule. Now, but this molecule will be very small. If you see oxygen, liquid oxygen, there will be have tons of oxygen molecules. They are also tied together by some force. So, for example, I have one oxygen molecule. There are so many oxygen molecules. They are tied together by some force, and that force is called van der Waals force. We will discuss this in the next chapter. So, if you're not understanding this, hold on. We'll have a clear understanding of this in the next chapter. So, with van der Waals force, we have van der Waals radii, and this represents overall size of atom. For example, if you see, there are two independent oxygen molecules. This is molecule 1 and this is molecule 2, right? So, if you see, these two molecules are totally independent, but they are held by some van der Waals force, right? And now if you see this radius, if you talk about this radius here to here, and you divide by 2, you get this radius. This radius is my van der Waals radius. So this represents the whole atom, and this covalent radius represents the atom's core. Hope you understand with this figure. So because the covalent radius represents the atom core and van der Waals represents the whole size of atom. So when we talk about bond length, we talk about the covalent radius, because we want to add this and this. If it is suppose hydrogen, this is chlorine, so the bond length will be, you want to add the covalent radii of the two atoms, not the van der Waals radii, because the covalent radii represents atom core and the van der Waals radii represents overall size of atom, right? There is something called ionic radii also. In case of ions, they are in case of crystalline state, they are separated by, they have some space, and they have coulombic attraction that binds them, and that is ionic radius, which we'll again discuss more in the next chapter. And then we have something called metallic radius also. So when we have metal bonds, as I told, metallic bonds are there, so they are held by a metallic radius. So we'll discuss all these in the next few slides, next chapter actually. For this chapter, just understand that we are concerned only for the covalent radius. And since we are concerned only about the covalent radius, here is the covalent radius given for some of the case. Hydrogen, if it is 37, carbon, if it is single bond, is 77, double bond 67, triple bond 60, nitrogen also for single bond 74, double bond 65, triple bond 755. Similarly, oxygen, single bond 66, double bond 57, fluorine has 64, picometer as a bond length, chlorine has 99, and so on. So if you don't need to memorize this chart, just the information I told that chemists have found these values experimentally and has provided us these values so that we can understand these atoms and molecules in a better way. So after bond length, the next parameter I told was the bond angle. This defines the angle between the orbitals containing the electron pairs around the center line. For example, if you see the hydrogen molecule, it has the angle of 104.5 degree, and this value also they got from the experiment using the spectrometer or X-ray and all these techniques. They actually saw this molecule and saw the angle between hydrogen and oxygen to be 104.5. So bond angle is nothing but angle between orbitals containing electron pairs around central atoms. and it is expressed in degree, and which can be experimentally described using spectroscopy. This helps in determining shape of molecule. Please note, this helps in determining shape of molecule. The next parameter I told was the bond enthalpy. This is nothing but the amount of energy required to break 1 mole of bond of particular type between two atoms. So you have, let's suppose, oxygen, liquid oxygen. You want to break this and make it 2 oxygen atom in a gaseous form. This is liquid, let's suppose. So the energy required to break this liquid into oxygen, that is the bond enthalpy. So the unit of bond enthalpy is energy, is kilojoule per mole. For example, HH bond enthalpy is 435.8 kilojoule per mole. This is the experimental value. That means if I have hydrogen gas, if I have to, this is a molecule actually. If I want to convert this into 2 atoms, put it apart at infinite distance, this much energy, 435.8 kilojoule of energy will be required to break 1 mole of hydrogen molecule into atoms. So in case this was for the hydrogen kind of stuff, for polyatomic molecules, for example H2O and all, it is more complicated. Things are a little complicated. For example, in case of water, if you see, for H2O I need 502 kilojoule per mole to take out first hydrogen. To take out second hydrogen from the same remaining OH molecule, to take out second I need 427. So in that case we talk about the average bond enthalpy. Correct? Because in the case of polyatomic molecule, if you see, things are little different. So to break the first, to take out first hydrogen, it takes more energy. Take out second hydrogen, it takes less energy. So what we do, we take out the average of this and use it. Then we have something called bond order. Bond order is something which has various definitions. So in case of the Lewis description, I'll use now, because till now we have this studied only the Lewis description. The bond order is nothing but the number of bonds. But we have more definition for this. I'll take this later when we'll discuss the other theories. I told that there are 4 theories. Out of this I have covered only 1. There are 3 more theories. The molecular orbital theory gave a different definition for bond order. We'll explain this when we go for a molecular orbital theory. In fact, we'll have one question in the end which we'll have, where we'll define the bond order based on different theories, right? But for this Lewis theory, the bond order is nothing but the number of bonds. For example, in H2 there is 1 bond, N2 like there was triple bond, O2 there was double bond, right? So in this case the bond order is 1, in this case it is 3, in this case it is 2. Correct? Also note that isoelectronic molecules which have same number of electrons have identical bond orders. And with the increasing bond order, the bond enthalpy increases. Why? Obviously because, as I told, right, carbon-carbon single bond, carbon-carbon double bond, carbon-carbon triple bond, the bond enthalpy, the bond length decreased. I don't have the correct values, but if it is this x, this was x minus y, and this is x minus y minus z, right? I'm talking about the bond length, and the enthalpy increased actually. Enthalpy increased. If it was A, it was A plus B, it was A plus B plus C. Here all x, y, z, A, B, C are positive. I don't have exact values, so I just use this x, y, and z. So carbon-carbon double bond, single bond was the bond length was x. Carbon-carbon double bond, the bond length decreased. Carbon triple bond, the bond length decreased further. But if we talk about the enthalpy, the energy required, so this increased. Carbon-carbon double bond, single bond required A energy, carbon double bond required E plus P energy, and carbon triple bond required E plus B plus C energy. So this is something we have seen. So these are linked actually. Bond order, bond enthalpy, bond length, everything is linked. Just to understand the bond properly, we are trying to understand the various properties of bond order. Thank you. Visit examfear.com to watch free educational videos, try free online tests, get the best quality study materials, study from the best tutors and mentors, and much more. Thanks once again.